Everyone good to go?
Yeah.
Cool.
Yeah.
All right. So, in our last lessons, we have been talking about linear growth and decay. And so with linear growth and decay, we know that we've been talking about things that are going up in a straight line or down in a straight line. Yep. All good? Everyone know what I'm talking about? Cool. All right. Gigi, can I ask you to put your laptop screen down for me? Thank you, just so I know you're concentrating. All right, so today we're talking about geometric growth and decay. So geometric growth and decay is when, geometric growth is when a quantity increases by the same percentage, or same percent, at regular intervals. And geometric decay is when a quantity decreases by the same percent at regular intervals. So what we're talking about, it's similar sort of calculations that we're doing, but instead of talking about linear, we're talking about geometric. We'll get into what that looks like in a moment. So it's really similar to linear growth and decay, but it increases by a set percent rather than a set value. So that's the biggest difference. Yes, it's still increasing or decreasing, but when we talked about linear, it was increasing by the same amount every single time. So plus 2, plus 2, plus 2, plus 2, plus 2. Or take away 2, take away 2. And it was going up and down by the same amount. Make sense? Whereas when we're talking about geometric, we are multiplying. And so because we are multiplying by a certain percent. So what we're going up by is a percentage. So if we're multiplying by 2, that's what we're multiplying up by. We won't divide because we'll be multiplying by decimals instead of dividing. Does that make sense? So it's just what we're going up by is a bit, it changes the form of what it looks like. All good so far? Cool. All right. So we've seen a recursion relation before. This is a little bit different, only because this is for a geometric recursion. So the biggest difference here is that we have R next to the Vn. So with our linear, we had the Vn, so that should be familiar for everyone. We've got our V0, which is what we're starting at. But this time we have an R instead of, what did we have in linear?
D.
Yep, we had D. So A is still our starting value. And R is what we call ratio. And it has the same sort of function as what D does, except instead of adding or plussing, we are multiplying. So when we're multiplying, So when we're multiplying, we call it ratio. But pretty much it does the same thing as what D does. It tells us what we're going up or down by. Does that make sense? We've just called it a different letter. Yeah.
So when you have a ratio, you're always timesing.
Yes. Does that make sense? So the only difference is we're multiplying, we're going up by a percent, we have a ratio instead of a difference, and this is our formula, rather than Vn plus or minus D. It will always be R times Vn. Whether we're increasing or decreasing, it will be the same recursion formula. All right, can I move down? Yep. Oh, too far. I'm really good at doing that. All right, so let's have a look at this table. And we did one of these tables really similar when we talked about linear recursion. So if you put this next to your linear one, you'll be able to see how they are similar and how they are different. So I've pretty much copied and pasted and changed the words because it's the same sort of calculations we're doing, but we're just doing them a little bit differently. So our results will be a little bit different. So, same thing, we've got a recurrence relation. So, it's saying P0 equals 1, Pn plus 1 equals 3Pn. So, this is saying we are starting at 1. Exactly like it was with our linear. Alright? P0, V0, T0, whatever, that is always what we are starting at. Exactly the same as when we did our linear. This is telling us what? What are we doing? Yep. We are multiplying by 3. So that is the rule. This bit here is telling us we are multiplying that term by 3. Yep.
When it says figure out for like 3 years or something,
Yep.
1, 2, and 3, is P0 classified as a year?
No, that's classified as a starting value. Yep, so if it says do it for years 1, 2 and 3, it wants P1, P2, P3.
Okay.
So you should have 4. Yep. Alright, so the sequence will look like, we'll start at 1, because that's our starting value, and then we're multiplying by 3. So 1 times 3 is 3, 3 times 3, 9, 9 times 3, 27, and it keeps on going. Does that make sense? Yep.
When it's the first 3 terms, you don't include the first starting term.
Yeah, so if asking for 1, 2 and 3, don't include the 0.
Would you write it though?
Yeah, you can still write it, yep, but it still wants V1, V2, V3.
Okay.
Alright, so same sort of thing, but instead of adding or subtracting, we're multiplying. Making sense? Cool, alright. Then we have our graph. What is our graph going to look like? It will increase, yep. And it's geometric, so what that means, if these are our terms down here, so we've got 1, 2, 3, 4, so remember these are our terms, I should have 0 there, so we've got 0, 1, 2, 3, making sense? Haven't confused anyone? Cool. Alright, let's go up by scale. So remember this is a scale, not what I've got here, so let's just say I'm going to go up by 5s. Okay, so for 0 we're starting at 1. For term 1 we're going up to 3. For 2 we're going up to 9. 3 we're going up to 27. So what this should look like, it should look like that. It's got a curve in it that's going up. You might not be able to see it with those dots, but that's what it should look like. Any questions about that? All good? All right. And if we're looking at the next one, so same thing. This is saying we are starting at 8. That's what our sequence is starting at. And we are multiplying by 0.5. So this is what I mean by we're only multiplying and not dividing. So we'll see that our numbers will start to decrease because we multiply by a decimal rather than divide by a whole number. Does that make sense? Yep, cool. All right, so we'd be starting at 8. And then we've got 8 times 0.5. 4 times 0.5. 2 times 0.5. All right, and we're just continuing that on. Any questions?
Will it
All good?
always be a curve?
Yes, for geometric, yes. So, same thing. Oops, that wasn't a very good scale. Wasn't a very good scale at all, but... Alright, so, starting at 8, 4, 2, the next one will be 1, and so it should start, oops, that's not very good, should start to look like that. Any questions? So that's the difference between our geometric and our linear. Our linear is straight, it's going up by or down by a certain number. Our geometric is curved and it's going up or down by a certain percent of the number of each term. Any questions? All right, so we can see that when R is greater than 1, so when our ratio that we're multiplying by is bigger than 1, it increases. And when our ratio is less than 1, so when it's a smaller number, our sequence should be decreasing.
Do we join the dots?
No, just leave them as dots. I've just drawn it like that just so you can see what it should be looking like, because my graphs aren't to scale, it might be a bit hard to actually pick what it's trying to say. Okay, because we're talking about finance, it's really important to note that when we're talking about simple interest, we're talking about, oh my goodness, I totally went blank then, arithmetic sequences. When we're talking about compound interest, we are talking about geometric sequences. So simple interest, we go up by the same amount, because simple interest, we calculate how much we're going to go up or down by on our principal value. So the first amount of money we have, we calculate what we're going to go up by. If it's $200, then we keep going up by $200. If it's $50, we keep going down by $50. Whereas compound interest, it's calculated on every single time we put money, or every time we've got money in that bank, or every time we need to pay back the loan. Does that make sense? If we're investing something and we start with $2,000,
So that's the same percentage?
yes. So if we start with $2,000 and we're going up by 5%, then $2,000, 5% of $2,000 will be added on that. And then we'll go up by 5% again. So 5% of $2,000 of that new value is what we go up by. And we'll go through that a little bit more today as well. But that's the difference. Simple interest is arithmetic, compound is geometric. And we'll go through compound interest in more detail. Any questions? Cool. Can I move down? Yep, all good? Everyone's got that? Cool. Alrighty. So, compound interest is calculated on each term rather than the starting value, which is what we do for simple interest. When we're using compound interest or geometric, when we're talking about something going down or decaying or depreciating, our R value will always be 0 point something, because it's got to be less than 1. If we're talking about growth or investment, it's usually going to be 1 point something. And that's what we're going to be going up by. When we're talking about using compound interest, our recursion relation is exactly the same whether we're investing or depreciating. It's exactly the same. The difference is how we find our ratio. So what we're going up or down by. If we're talking about investment, which is increasing, we have a plus in our formula. If we're talking about going down or depreciating, we have a takeaway. Any questions?
Do we have to write anything we agree with?
No.
Okay.
Just saying it'd be 0 point, or 1 point, Yep. Okay, so if we're given a rate of something, if we're investing something at 4.8% per annum, we need to do this to find the ratio that we're going up by. If something is depreciating by 4.8% per annum, we need to do this to find what we're going down by. Does that make sense? We don't put the 4.8% into our equation. We need to do this first.
And then put it in?
And then put it in, yep. And we'll go through some examples and we'll see how that works as well. But it's important that you do that first. Like when we were using our linear recursion, and we were talking about if something was going up by 4.8% on simple interest, first we had to find the D. Once we found the D, then we put that into our recursion relation. Does that make sense? Same thing, but we're talking about compound interest, so we're using ratio. All good? Yeah? Cool. All right. So usually rates will be given as per annum, which is? Yep, per year. If a rate is given as per annum, but is not compounded yearly, so such as monthly or quarterly, we need to divide the rate by how many times it will be calculated per year. And you need to do this before we put it into, or when we put it into our R formula. And we'll go through a few examples as well. So sometimes it might say, you might get a question where it's investing, compounding, or an investment that's at 4.8% per annum, compounding monthly. So it's saying the rate per year is 4.8, but we're calculating it monthly. So we've got two different things. We've got per annum and we've got monthly. So we need to do this sort of conversion. Okay, well, what is it getting calculated at monthly if it's 4.8 per year? So that's what this is doing. So if your question is talking about quarterly, we're going to divide by 4. If it's monthly, we're dividing by 12 because there is 12 months in a year. And if it's daily, it's going to be 365. So we have 365 days per year.
Is this a replacement of the over 100?
No, so it will still have the 100 in there as well.
So
it would be like 4.8 divided by 4 divided by 100. We'll go through some examples as well. Yeah. Usually when we're doing daily, or at the moment when we're doing daily, we're not going to, if we're talking about 3 years compounding daily, we're not going to take into account leap years. We're just going to leave it as 365. Right? At the moment, that's what we're doing. Any questions? Cool. All right, let's get into some examples so then we can actually put what we've learnt into practice. Can I move down? Yep.
Can I ask a question?
Sure.
So is geometric only compound?
Yes.
And then the other one, linear is per
Yes. Okay, so the example we have, the following recurrence relation can be used to model a compound interest investment of $2,000 paying interest at the rate of 7.5% per annum. So they've given us the recurrence relation. They've given it to us, they've told us what our starting value is, and they've told us what we have to multiply by. We can see that this number is different than this number. Alright? This number has already been put into that R formula. They've given us the ratio, they've given us what we need to multiply by, and we can see that because it's in our recurrence relation. So if it's in the recurrence relation already, you've been given the recurrence relation, this number is here, that's what we're multiplying by. You don't need to put anything into the R formula. Make sense? Yep, might want to make a note of that.
If there wasn't if it just was the R, you'd have to find it.
Yeah.
But with that rule, it's got R over 100. How
Yep.
can you find it if you don't know what it is?
We don't need it. It's given to us
But
in
if
this
it's not
one.
given.
Yep, we'll go through some
Oh, okay.
examples like that in a moment. Okay, so the question says, use the recurrence relation to find the value of the investment after 1, 2 and 3 years. So we already know that at the start, after no years, we've got $2,000. So we've walked up to the bank and we've gone, here's $2,000, invest it. That's after no years. That doesn't take us a year to walk into the bank and put the money in the bank. If it did, well, we'd be having a boring life. All right, we go up there, put it in, it's done. It's 0. That's what it's starting at. That is no years. That's why it's 0, not 1. Make sense? Okay, nothing has been done to this number. So V1 is saying, okay, it's been sitting in there for 1 year. Now what does it equal? So when we're talking about V1, we're talking about after 1 year. Does that make sense?
Will it always be years?
No.
Oh, like the month.
The
It
month,
always
yeah.
be like time.
Yes, always time, yeah. All right, so we are using our recursion. So this is the one we've been talking about where we've got the R times Vn. So the R that we're using is 1.075 by the previous term, which was 2,000.
Do we have to write it all like that, or can we just?
No, if you just want to go straight to this step, that's okay. Yep, I'm just putting it in so you know where I'm
Is
at.
Do we have to even write that?
Yes, you have to show that you used recursion.
Is Vn just the next term?
Yep. So after 1 year, we have $2,150. After 2 years, so we're putting in this one down here now. Oh, that was a funny looking one. So after 2 years, we have $2,311.25. So after 3 years, using this number up into here, and we'll have one.
So if we write like V3 equals RV2.
Actually, technically we should be. Yeah, you are correct. Yep. That's the term before. Yeah, you are correct.
Doesn't matter. Or should you write it like that?
Technically, that's more correct.
Okay.
I'll have to double check that. I'll have to go through last year's.
So you said we didn't really need to write that anyway.
Yeah, I did say that, didn't I? Yeah. So, yeah. Yeah, if you don't write that, then it doesn't matter. Yeah. All right. So then our third term is $2,484.59. Because we are working with money, we should always have no more than 2 decimals, because we don't have, 25.6 cents. It's only, 25 or 26 cents. Does that make sense?
So if it doesn't
Cents?
ask,
Uh-huh. Hey?
if it doesn't ask, then
Just do 2, yep. Because we're working with money. So we can see with these numbers how they differ from using simple interest as well, and what we're increasing by. So we can see that from 2,000 to 2,150, we've gone up by $150. If we were using simple interest, then the next one would be up by $150. Then the next one would be up by $150. But when we're using compound interest, we can see that this doesn't go up by $150. It goes up by more. Does that make sense? So that's what happens when we use compound interest, and that's why it goes geometrically rather than linear.
Same percent.
Yes. Yep. By this. Yep. By 7.5%. Any questions about that so far? Okay, so determine when the value of the investment will first exceed $2,500. If we're talking about recursion, we need to keep using recursion. So, V4 is $2,670.93. So that was our next term. So after 4 years, the investment will be more than $2,500.
If we just write the second thing, is that okay?
Just wrote that. No, show what V4 equals. And then it's justifying your answer.
And we don't have to round up to like 5 cents.
No. No, unless it tells you to.
Since it just says determine and doesn't say determine and justify, could you just say V4 equals?
I would write a
Always
sentence.
justify.
Yeah, just write a sentence. It's not going to take you that much to write a sentence.
So you have to keep doing it by hand.
Yeah, if we're talking about recursion.
Okay.
Yeah.
There's no way to like put in the calculator and press enter.
Just keep, so put your first value in.
Yep.
Remember how we did this on the calculator?
Yeah.
Then press enter, then put times this, and just keep pressing that and just count how many times you
Okay.
pressed it.
Yeah.
Yeah. And if you record it, then it makes it easy too. Any questions? Can I move down? Yep.
But then don't you, if you do it on the calculator, don't you then keep timesing it by something new? Like so you put that.
No, so you're timesing it by the same thing, but the number you're
So
timesing
you
it on
just
is
put
another.
like that and then press enter and then
Yep, yep, and then put times 1.075.
Yep.
Yep. Okay, so write down the recurrence relation if $15,000 was invested at a compound interest rate of 6% per annum. All right, so what we need to do to this is we can start with our V0. We know what that equals. Equals 1,500. We haven't been given the ratio. We've been given the percentage. So we need to turn this into our ratio. So to do that, we need to use our R formula. Making sense? We are investing, so it should be increasing. So we need to use the 1 with a plus. So our R will equal 1 plus the rate over 100. So that would be 1 plus 6 over 100. So our R equals 1.06. All good so far? So then, when we write our recursion, $1.06 billion. Any questions about that?